Now go to section 3, 9.3. It becomes second order. Second order. In this case, you have the first case is only have you have two variables, and then only two second derivatives. Right, that's like what we call a standard form, and later on we'll have a more. Adding a cross term, and there will be exercise to show that you can transform one to the other. So this one is you have a square plus a square plus x square, and then minus c square. To solve this equation, and again, that's we are doing a constant coefficient at first, right? In this case, because of the simple form, we only have a second derivative. We don't have all these first derivative, and also not the cost. You don't have partial square, partial x, partial y. You don't have that, right? And one straightforward way to do that is doing a factorization. This treating it like a polynomial. Just a squared times x squared plus these minus c squared times y squared, and factor that. You know how to factor that, right? So that becomes a partial x c partial y, and then a partial x minus c partial y. Operate on phi. Right. Then it's quite straightforward, right? It's like your algebra, but using differential operator. But you can check that, right? That's like what we did for algebra. Just multiply it together. So this times that will give you this one, right? Because we assume that these are constant. If this is not constant, obviously you have trouble. You get into trouble because this way, and when you write it like that, this differential operator also operate on a. If a is a function of x and y, then you obviously get into trouble, right? But assuming constant coefficient, this times that is this one, this times that is this one, you have the minus sign, right? And then this times that plus this times that will be 0 because the coefficient both a times c, one is plus sign, one is minus sign, and you have a second derivative, partial square, partial x, partial y, so that cancel. So that obviously this one. Now once you write like that, so you can use the solution in the previous section to separate that into two solutions. So you have two solutions, phi sub 1 and phi sub 2. So you can say that is partial phi sub 1, partial x, c, partial 1, partial y equal to 0. And another solution is a partial phi sub 2 minus c, either phi sub 1 and phi sub 2, you plug it in, will be 0, will satisfy 0 because you just using one factor to operate on that, and that will kill kill the whole thing. And so a general solution will be some combination of phi sub 1 and phi sub 2, right? And you have two solutions. In that case, and you know how to solve this, right? Just what we did before. And so, and that's one case. All right. Yes. And to connect to the next discussion, actually, we should write the solution out. Right, so one is equals to some general function of just like what we did before. As the solution is that c times x minus a times y. Just use the result that we first talked about in the last section. And likewise, for instance, 2 will be some g function. Any general function will be a solution of that. Okay, and now the next discussion is changing this sign. And at first, you might be wondering why we choose a negative sign at first, because the negative sign problem will give you a solution. We'll have a solution of this form. This is what we call the hyperbolic problem, because if you treat this like this, this variable is a squared x squared minus c squared y squared equals to a constant, that would be the equation for a hyperbola, generally hyperbola. Then that kind of form is called hyperbolic equation. And for the next one, it changes the plus sign. And you see that the solution is different. Right, and then again, this, if you treat it like x squared, this is y squared, that is generally an equation for ellipse. If this is equals to a constant, then generally an equation of ellipse. And so the equation will be elliptical. It's called elliptic, right? Then following the same way to factorize that. And what we see is that you factorize that, this c, in order to write exactly the same form and to get the positive sign in the second term, you need an imaginary number here. So c becomes imaginary, because this time set is minus c squared, right? So in order to get plus c squared, you need I times I becomes minus sign, right? So and plus I c plus 1, then a minus I c. 5 is 0. Okay, although now you can still put it in the form of the form that we talked about in last section. It's still constant coefficient in 2 variables, but the major difference is that now the coefficient is not real. Assuming C, all this A and C are real number, that becomes a compact coefficient for this first order ODE. I mean, the solution becomes imaginary. So it's basically now the changing C, the IZ, that becomes you need to go to the complex plane to finding compact solution. And if you are looking for solving physical solution in the real domain, then that becomes a problem. So it means the elliptic solution has slightly more difficult to solve, right? And so you need to treat the 2 cases differently. So to find a real solution for this one is you need something else. You need to solve something else. Okay, so the general idea is first to recognize or differentiate what the differential operator in the form, whether it's hyperbolic or elliptic, and that make a difference in solving a differential equation. And that can be generalized to, like again, generalized to higher dimension and also variable coefficient also. And one more case is so-called parabolic. So you have hyperbola and ellipse for this one. And one special case that we call hyperbolic is A times. It's just one derivative, first derivative on x, and then second derivative on the other variable. That is what we call the elliptic. So you have three kinds. So you have hyperbolic, elliptic, and parabolic. Right? And now how much time we have? So let's write down the final form of this differential operator. That can be put into this either hyperbolic or elliptic. So write it in the form that includes not just the second derivative xy, but also the cos term. You have a also square 5 also x squared, and then the cos term has a definition of 2 in here in the coefficient, just for convenience to write down the formula. Plus x also y. Let's see. Also square, also 5 y squared. Right. And again, treating it like algebraic equation, so ax squared plus 2bxy plus c y squared, right? And you can factorize that. And the factorization involves just like solving a second order algebraic equation, right? A quadratic algebraic equation. And you know the solution, right? And you can work that out or by just multiplying out explicitly. So the form is like your solution for quadratic equation, so b plus b squared minus ac, right? Usually you have our choice. Originally, usually there's a 4, but because of your choice of this factor of 2, you just have this b squared minus ac instead of b squared minus 4ac. Right? Then divided by c, this is 1/2 x of c plus y, and then minus a times c by, right? Again, to check this, whether this is the same of that, one way to do it is just by, I forgot this part. Just treat this like variable, because these are assumed to be constant coefficient, and then just multiply together, and this times that, and work out the product like this times that. It's just use the a plus b times a minus b formula, and then figure out that that will give you the first coefficient, and likewise this times that will give you this one, and then the cross product, this times this, and this times that will give you this one. With just direct multiplication, and that check is quite elementary, so you can check that yourself, right? And so that is again, this fact you can factorize that in the 2 ODE, and the idea is now that whether you have a real solution now depends on whether the square root is real. So, and whether square root is real depends on the inside the square, whether positive, negative. So if b squared minus ac is positive, or positive, or even 0, right? But a 0, I think 0 will give you a parabolic. If it's positive, then these are all real. The square root is real, the coefficient is real, then you get this, just like what we did the first case, the minus case, right? That's hyperbolic. So b squared, this is hyperbolic, right? That's elliptic. So because now this is negative, so that's it, you get an I out. You get an I down here, so this is elliptic. Right, and then if it's 0, I think what you multiply out together, you get something parabolic, right? Okay. Anyway, this factor is in the general form. When you write it, define your ABC this way, then that is a quantity that will determine whether it's hyperbolic, elliptic, or parabolic. Okay, and finally, there will be a form in 9.21, make it like a change of variable. But that would be a homework question. So you work with that. So and then this factor with a negative sign will go into the coefficient of one of the second derivatives. Okay, and I think that's all. After you work out the homework problem, which is quite straightforward, and then you know that can transform to the standard form. So this form can transform to this standard form.